Okay, so you may or may not have figured out an answer to this question. How many different outfits can you make given you have a pair of khaki pants, a pair of jeans, a pair of shorts, one button-down shirt, and one t-shirt? So essentially 3 pairs of pants and 2 different shirts. So we want to figure out how many different combinations of these exist. So one way to approach that question is to make yourself a list, make yourself a tree diagram, kind of similar to the chart we used the other day. So if you think about the pants that you have, the options for pants, we can make ourselves a list. We can say, well, I can either wear khakis, or I can wear jeans, or I can wear shorts, abbreviated as you just see it. So those are my 3 options for pants. And then I make a choice for the pair of pants I'm going to wear. I'm going to have 2 options for shirts for every single pair of pants that I gave myself. So, for example, I'm going to say with my khakis, I could wear a button-down if I wanted to. With my jeans, I could also wear that button-down. And with my shorts, I could also wear a button-down. Or I could go the other route, and I could keep it a little more casual, and I could wear a t-shirt with my pair of khakis, or I could wear a t-shirt with my jeans, or I could wear a t-shirt with my shorts. Probably the most casual of them all. Well, if you think about it, if you start from the beginning and follow the branches to the end, we are going to end up with 1, 2, 3, 4, 5, 6 different combinations of outfits. Now, it doesn't matter how you make your tree. I could just have easily started with the button-down or t-shirt as my first branch of the tree, and then I'm going to split it up 3 times for each of my pants combinations, because then I could say khaki or jeans or shirts for each of those combinations. And again, main idea right here, it doesn't make a difference. I'm still going to end up with 1, 2, 3, 4, 5, 6 options. Now, some of you may have noticed that this is like saying, now I'm actually going to change my train of thought right there. I'm going to pause real quick, and I'm going to ask you to create your own counting tree for the problem that I'm about to show you. There is an ice cream shop in town, and for, let's say, $2.50, they offer you a pretty good deal on a sundae, and you get to build your own sundae. You have 3 choices for the type of ice cream, either vanilla, chocolate, or strawberry. And then you have 3 choices for a topping, either caramel sauce, chocolate syrup, or whipped cream. And then finally, they offer you 3 options for a finishing touch, either sprinkles, cherries, or peanuts. And cherries is probably spelled with an I-E-S. I don't know. That's why I teach math. So we want to know what are the total number of different possibilities of sundaes that you could make given these options. Now this is going to work just like the last one. I will go ahead and get you started. Think of it in terms of 3 different stages. You've got the ice cream phase, the topping phase, and then the finishing touches phase, which I will abbreviate FT. So, for ice cream, we've got some options. We've got vanilla, we've got chocolate, and we've got strawberry. Now, once you make that option, think about for vanilla, if you chose vanilla ice cream, we're going to have 3 different toppings, 3 different choices for toppings, and 3 different choices for toppings if you chose chocolate, and 3 different choices for toppings if you chose strawberry. Go ahead and finish this tree out, branch into the topping section, and then go into the finished touch section. And I want to know how many total different possible sundaes could you create given these options. You have 2 minutes. Go. Okay, so you should have continued your tree, and you should get pretty messy pretty quickly because there are tons of options here. We did our first stage already, choosing the type of ice cream, vanilla, chocolate, and strawberry. But then we move into the topping phase where we have 3 options for each of our already 3 options. You can either get caramel sauce, chocolate syrup, or whipped cream for each of those options. So we add a lot right there in the beginning. And then for each of those 3 new options, we have 3 options for each finishing touch. And if you add them all up, you can just count our last column there, and we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Holy moly, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 20, 20, oh my gosh, 24, oh goodness, 4, okay, I'm trying to write 24, 25, 26, and 27 total options, because imagine it, you can follow one of those paths all the way down, and that would give you 1 option. There are 27 total combinations of ice cream sundaes you can make given these limited options. Now you can see as the number of options at each stage increases, this is going to get messier and messier and messier to do, and it quickly becomes impractical to actually list all of the options out. But let's jump back a page and look at this simplified example. If you recall, we had 6 options for outfits that we can wear. But let's look at how we can make this a little bit less painful a process. Notice that if we look at our first example here, we have 3 options in the first stage, and then at our second stage, we have 2 options. And we had 3 times 2 equals 6 total possible outcomes. Now notice that's like saying we had 3 groups of 2 items each, 3 times 2. Well, it worked the other way too. We started with 2 groups, either our button-down or our t-shirts, and then at the second stage we had 3 options there. So we had 2 groups of 3 items each for, again, 6 options. So we can make it much simpler on ourselves here because we had 3 choices at the first stage, 3 choices at the second stage, and 3 choices at our final stage, our third stage, to give us 3 times 3 times 3 equals 27 total possible outcomes. This is called the fundamental counting principle. What it says is that if you have m options for the first event, n options for the second event, you can multiply them together to get m times n possible ways. For example, if you have 3 pants and 2 shirts, we can take 3 times 2 to get 6 possible outfits. That's what we already showed. Go ahead and read and try to solve this problem now. We're told that license plates in Maryland in 2004 were composed of 3 letters followed by 3 digits, And in 1912, license plates in Maryland were composed entirely of just 4 digits. We want to know how many more license plates in 2004, possible license plates in 2004. Okay, let's try this again. How many more 2004 style license plates were possible than 1912 style license plates? So basically, how many more possible combinations do we have in 2004 than we had in 1912? And remember that we've got 26 letters in the alphabet, and we have 10 digits at our disposal. Disposal? Okay. Don't forget that 0 is an option for digits. So go ahead and try to answer this question. You have 3.5 minutes. Go! Alright, so in answering this question, we have 3 different pieces we need to figure out. First off, we need to determine the total number of options for a 2004 Maryland plate. To do that, well, look, we've got 3 letters followed by 3 digits. Now, for the first letter, we have 26 options. For the second letter, we also have 26 options, and for the third letter, we have, 26 options. And then we have 10 options for our first number, and 10 options for our second number, and 10 options for our third number. So we are multiplying the number of possibilities at each stage of the game all together. 26 times 26 times 26 times 10 times 10 times 10. And that number, which should be, I believe, 17,576,000 options. And we need to compare that to the number of possible license plates in 1912. Well, for that, it's a little bit simpler of a calculation because we have 1, 2, 3, 4 digits, and that's it. So we have 10 options for the first digit, 10 options for the second digit, 10 options for the third, and 10 options for the fourth digit, and you should get 10,000 possibilities there. So to answer the question, how many more, we need to take the difference, and we need to take 17,576,000, and we need to subtract, so that number being the total number of possible plates in 2004, subtract the total possible plates in 1912 to figure out how many more there are in 2004. Do that, and you should get 17,566,000 more possibilities in 2004 than existed in 1912. Woo! Go ahead and take 2 minutes to answer this question. In 1966, one type of Maryland license plate had 2 letters followed by 4 digits. How many of this type of license plate were possible? Wow, I can't talk today. How many types of this plate could you make? Go ahead and figure that number out. 2 minutes. Pause. Okay, hopefully you paused. If not, this is going to sound silly. Anyways, we want to figure out the total number of possible plates here. So we know we have 2 letters followed by 4 digits. So we're going to get letter, number, number. Well, there are 26 letters in the alphabet, so we're going to get 26 times 26 times 10 times 10 times 10 times 10, because there are 10 possible numbers for us to choose from, 0 through 9. So multiply that all together, and you should get, let's see, what is that number? 6,760,000 possible license plates following that scheme right there. Cool. Moving forward. So let's continue our exploration into probability. A new term we have is called a permutation. Now, a permutation is just an arrangement of items in a particular order. Suppose you wanted to find the number of ways to order 3 items. Like, say, for example, 3 people are having a race, and you want to figure out what are the possible outcomes of the race, i.e., who got first, who got second, who got third. Let's use that as our example. Now, notice this particular word, particular. That is very important to what a permutation is. That is the key piece you need to know. A permutation is an arrangement of items in particular order, meaning the order of the items matter. For example, it makes a difference if you get first compared to if you get second. The order in which you finish matters. That is going to be a key difference between another term we are going to learn next time we see each other. Suppose you wanted to find the number of ways to order 3 items. There are 3 ways to choose the first item. So, for example, let's say we've got Lenny, Bob, and Tim are racing each other. Well, Lenny could get first, and if Lenny gets first, then Bob could get second, and Tim could get third. Or Lenny could get first, and Tim could get second, and Bob could get third. Okay, well, once Lenny is chosen, we see we have those 2 different possible outcomes for second place, because Lenny is removed from the situation. Well, once that is chosen, once the second person is chosen, they each only have 1 possible outcome. Once second is chosen, third is essentially fixed. So we've got 3 options for the first one, because we could have gone Bob got first, and then maybe Lenny got second, and Tim got third. Or Bob got first, and Tim got second, and Lenny got third. I'll draw it like that. Bob, boop. Or maybe Tim got first, and then we're going to have Larry and Bob and Larry in that fashion. Again, it's the same idea. We're going to end up with a total of 6 possible combinations here. Or 3 options for the first case, 2 options for the second case, since we're down 1 person, since they've already gotten first place, and then only 1 option for the last case. So we get 3 times 2 times 1 is a total of 6 possible orderings, or 6 possible permutations. Whoop. Now, mathematicians have developed an easier way to write this. Because imagine if we had something like this, but if we started with 100 people and we wanted to list the 100 possible orderings of these people. Well, that would be a lot to multiply together. So we came up with this term called a factorial, and it's written with an exclamation mark, which is fun, and it is defined by that. So like 3 factorial, you start with 3, and then you multiply it by each integer below that to get a number, 6. 3 times 2 times 1. This n factorial here, all that's saying is n factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4, etc., all the way down to 3, 2, and 1. So if n factorial wasn't n factorial, but it was 5 factorial, we'd be saying 5 times 4 times 3 times 2 times 1. And then also here, notice that 0 factorial is defined as 1. So 0 factorial equals 1. Just a definition you're going to have to live with. So let's take a look at how we can use this idea of n factorial to actually answer one of these probability problems. So let's say we have 12 distinct folders, and we want to know in how many different ways could we organize these folders from first to last in a filing cabinet. Well, think about it the same way. You have 12 options for the first folder. Well, once you've chosen that first folder, that's now out of the bag for the next folders to choose. So, once you pull one out, then you have 11 options for the second, and then 10 options for the third, etc., 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 all the way down to that one last option. Well, rather than writing 12 times 11 times 10 times 9 times 8, all of that, I'm just going to write that as 12 factorial. Now, our calculator actually has a factorial button, and I'm going to show you how to do that. So please get out your calculators. If you do not have a calculator, you will need to share with somebody around you. There will be no calculator loaning today. So, go ahead and get those calculators out, and let's go ahead and show you how to do this. So turn your calculator on, of course, and then hit the math button. Hit the math button. Carl and Rachel, sorry, don't know how to do it on a Casio. I'm sure it's easy, just Google it, or I'll help you when I get back. Turn it on, hit the math button, and you should see a bunch of different options. At the top, notice the first column says math, second column says num, third column says CPX, and fourth column says PRB. We want PRB because we were talking about probability. So go to the probability column over there, PRB, arrow over to it using your arrow keys 3 times on the right or just once on the left. And notice that it's most likely option number 4 has a little exclamation point, and that is your factorial. So I probably should have told you first, if you wanted to do 12 factorial, first type in 12, then go to math, then go to probability, and then go to option 4, and it will print 12 factorial on your screen. Hit enter, and you should get the ridiculously large number 479,001,600 different ways to organize 12 folders. That is way too many ways to be able to organize 12 folders. That's ridiculous. Alright, so similar idea. Let's say you have 8 different shirts, and how many different ways could you order those in your closet? Go ahead and take 1 minute, maybe minute and a half, figure this out. Find a number, use your calculator, boobity boobity boop. Okay, hopefully you're done. Using the same idea as before, you're going to have 8 options for the first shirt, 7 options for the next one, 6 options for the next one, etc., all the way down to your last fixed option, which is just going to be 8 factorial. So hopefully you were able to get that in your calculator. 8 factorial is 40,320 different ways to organize those shirts. Again, like, that number is way too big. That's a ridiculously large number of options for only 8 things. Yet, it is the number of options. So, there you go. So go ahead and take a look at this next problem. 10 students are in a race. First, second, and third place will win medals. And again, it makes a difference if you're in first or second. You either get a nice gold medal or a kind of nice but not as nice silver medal. We want to know in how many different ways could these 10 runners finish first, second, and third. And we're just saying that tying is not a possibility for whatever reason. There's a head-to-head, they duel or something like that. Well, go ahead and try to do this problem. It's a very similar idea, slightly different. Take 2 minutes and go. And then we're going to derive a formula based off of this example. Okay. If you haven't done so already, this is your cue to pause it and do this real quick. But here's your solution. So think about 10 people are racing. So we have 10 options for first place. Once that first person finishes, then there are 9 people still in the race, and they'll have 9 different options of people who could get second. Similarly, we have 2 people gone, so now we have 8 different options for the number of people who are going to get third place. So multiply those all together. I'm going to do some mental math. 9 times 8 is 72, times 10 is 720 different possible outcomes for this situation. Notice this time it was not 10 factorial because we're not talking about the total number of possibilities for any permutation of finishing results. We only cared about first, second, and third. So, slightly different. But, check this out. Let's write this in terms of factorials, because then we can maybe come up with a formula that will make this a little bit more useful to us. So, to do that, let's pretend like we had done 10 factorial. Well, this is not 10 factorial. 10 times 9 times 8, it's the start of a factorial, but it's not quite there. So, if you think about this 10 factorial, what we really have is 10 times 9 times 8 times 7 times 6 times 5 times bop, 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 all the way down to times 1. But that's not what we want, because we're only interested in that first bit, 10 times 9 times 8. So we can make that other bit disappear if we divide by 7 times 6 times 5 times bop, bop, bop times 1. Because then, look, we'll have the same thing in the numerator and the denominator, so they'll just cancel each other out. They'll go to 1. And we're left with what we want, 10 times 9 times 8. Well, you may be like asking yourself, why is this useful? Well, check it out. We can write that as 10 factorial, and I should 10 factorial, that numerator, divided by, well look, 7 times 6 times 5 times 4 times 3 times 2 times 1 is just 7 factorial. That's kind of useful. That's a quick way to write it. But you still might be like, well, that's just still more work than just doing 10 times 9 times 8. Well, imagine you had like a really imagine you had 700 contestants and you wanted to know, well, how many different ways can people finish in the top 100? You're not going to want to write 700 times 699 times 698 times 697, etc., all 100 times. That would stink, and we like to find shortcuts as mathematicians. So that's one way we do that. So generally, we can say this. Look at this case. We had 10 factorial divided by 10 minus 3 factorial. That gets us, parentheses first, 10 minus 3 is 7 factorial. So that's the same thing. But look, 10 minus 3, oh, we had 3 specific places that we were looking for. We were looking for first, second, and third. 3 different options there. And that is actually our generic formula. N factorial divided by n minus r factorial, where n is the total number of options, and 3 is the specific number of different ways we are looking to arrange those 10 options. I kind of paused there. I'm not sure if that sentence makes sense. But n is the total number of items we're looking at, and r is the number of different ways we're looking to arrange those items. More formally, and yes, you need this in your notes, we write it as NP for permutation, R, and it's defined as how we just defined it, n factorial divided by n minus r factorial, and that is the number of permutations for n total items, and we're arranging those items 3 at a time. So like our example with the race, we had first, second, and third. Those are the 3 at a time options that we are interested in. So a specific example there, you can look at that. 10P4 is saying we've got 10 total items, and we are arranging them 4 items at a time. So we're going to get 10 factorial over 10 minus 4, which is 6 factorial. Pretty straightforward. Just need to remember which of those is which, but you should be able to work it out either way. So go ahead, take 3 minutes, 2.5 minutes, somewhere around there. Try to answer these 2 questions. First one, in how many different ways can 15 runners finish in first, second, and third? How many different ways could you give out those medals? And then answer this question. Is the number of ways for runners to finish first, second, and third the same as the number of ways for some runners to finish 8th, 9th, and 10th? And explain your reasoning. So take 3 minutes, try to answer those 2 questions. Really focus on that second one, though. That's a key idea there. Alright, so answering that first question, in how many ways can 15 runners finish first, second, and third? Well, following our logic from before, we're going to have 15 options for first place, 14 options for second place, and 13 options for third place. Using our formula, we are saying 15 permutations arranged in 3 different ways, which is going to give us 15 factorial over 15 minus 3 factorial. So we've got 15 factorial over 12 factorial, and I should probably get this number. 2,730 different possible combinations for that. Now, the second question, we want to know, is the number of ways for runners to finish first, second, and third the same as the number of ways to finish 8th, 9th, and 10th? Well, yes, it is. Because in both cases, you're just going to be taking a total of 15 runners and permuting them into an arrangement of 3 different places. 8th, 9th, and 10th. It doesn't matter that we happen to be looking at 8th, 9th, and 10th over 1st, 2nd, and 3rd. The number of possibilities are still exactly the same. Because we're not saying at this point that 1st, 2nd, 3rd, blah, 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 all the way down to 12th place is already chosen. We're just looking at it from a different point of view. So, at this point, go ahead and take a look at your homework. Again, whatever you don't finish will be due in class tomorrow. Now your worksheet should be coming out to you momentarily, and it should say 11-1, practice problems on it. And you are to do all of those problems. And I will see you tomorrow. Yay! And before I go, I just thought I'd show you a picture of where I am. This is currently what my backyard looks like, hanging out in Tennessee. Got the pretty hillside there. And TKO, graffiti everywhere, means Tennessee Knockout. It's a really cool race they do here. Hardest race in the U.S. So, there you go. See you tomorrow.